Okay, can we start? All right. So finally, let's get started on the basic geometry lecture. So this will be until the break for like an hour and a half, maybe less. It will be about basic geometry, how to approach the code in your geometry problems, what are the things that you have to know, the most common things. And after that, after the break, we will talk about more complicated geometry problems. So if you want to, you can stay for the second part of the lecture, or if you just want to listen about the basic stuff, then you can leave after the break. That's okay. We'll have two separate contests today, like the basic problems and then the harder problems, more in vein of the second lecture. You can choose any of them for your participation today. Okay, all right. So let's get started. The reason why I chose to cover this topic is because, as I said before, for some reason people are like afraid of geometry. They're afraid to, learn geometry, solve geometrical problems, and the thing is, you have to know the correct approach to them. In Russia, there was a joke that there are several different approaches based on from which city you are, because at least back in the days, I guess the learning approach was somewhat different. So in St. Petersburg, we'll call it that, the approach you would use is basically to solve everything mathematically. That is, you write down a lot of formulas, and usually if you combine all the formulas together, you can finally obtain a formula which is usually very long, that you can just plug into a program, and then you will probably make a mistake and will spend half an hour looking for that. So I know some people do that while they're not very experienced. In Moscow, they use they use another approach, which is I'll be covering, which is try to encapsulate most of your code. So, for example, if you have a certain type of objects, like a vector or a point or a line or a circle, you, instead of having variables, several parameters that describe that, like coordinates or coordinates and a radius, so you create a structure for that, and then everything you do, all the basic operations, are represented in terms of functions and class methods and so on. So this is a recommended method. I will elaborate on why. And in Saratov, as the joke goes, the approach to solve geometry problems is not to solve them, to ignore them completely. And, well, this is not an approach I would subscribe for. Okay, so let's start with how you should organize your code. And, well, I think we'll start with some actual material, and as we go, I will explain how you could better do it. So, we're speaking about geometry. Oh, should I turn the volume down? Let's see. Okay. So, geometry in the plane, right? And what is the most basic object you could have in the plane? The most basic, yeah. So we have a point which is described by two numbers, x and y, which are sometimes they're integer, sometimes you can obtain some points which have real coordinates, and depending on that, you may want to choose this appropriately. You have to take care of that. So the first thing is that we want to create a class for a point, and also another basic object is vector. But since it's described by the same two coordinates, we'll just going to use the same class for them. Some people go for having two different classes for a point and for the vector, despite the fact that like they will be mostly the same. That has to do with logic, because some things you can do with vectors that you cannot do with points, and so on. But okay, so for clarity, we will call our structure vector. My naming will be like this. So this capital T is type, which is some naming scheme to differentiate the names of types and classes from actual variables. So I call this vector because to each point we can associate so-called radius vector, which is the vector from the origin to our actual point. So this is a point, and this is a vector, and they are different objects. But nevertheless, we will instead of dealing with the point, we will think about this vector. Okay. So here we have two fields and probably something else. Okay. All right. So we have a vector, and we can do a lot of basic operations with vectors, right? Like, for example, addition. So if we have a vector and we have another vector, and then by adding them, we obtain, by triangle rule, we obtain a third vector, okay? So the formulas for that is that we just sum up the coordinates, like x separately and y separately. So since this is a very basic operation, we want to make a special function for that, or a method, because we are going to use it a lot. And this is an example of the approach basically that I'm advocating. If you have an operation that you are going to use many times, you want to have a convenient function to do that. So how do we actually do that? For example, we could go and write a separate function here, and then like sum of vectors, right? And we may write sum of P and Q here, if P is this vector and Q is this vector. But in terms of code, it will be much more convenient and concise to utilize operators overloading. I'm talking about C++ right now, but I think it's not too much different in other languages. So if you use Java, then a very similar thing, and you can do a very similar thing there. Which you probably know more about than me, because I don't know Java quite a lot. And in Python, you can reload operators as well. Again, if you are going to use it, you may try to look it up if you don't know how to do that. So basically, what we want to do is, instead of these, we just want to write P plus Q. Because, well, obviously, P is an object, Q is an object, and their sum is defined. And this is much more concise than this, because if you want to write a long formula like P plus Q plus R plus, I don't know, T times 2, for example, then if you would go with this function, it would get very long, like sum of sum of sum of sum, and this is much more concise. So how do we reload operators in C++? Basically, we create a special function here inside this structure, which is called operator plus. So a special name. So it returns, again, it returns vector, right? So we mark its return type as vector. And then here, we write down the arguments. And the thing is, since we are defining this inside the structure, the first argument of this P plus Q is already bound to be P. So we only have to define the second argument here. So we go with T vector Q. And you may want to write const here after this argument list to mark that this function will not change will not change the structure itself. It's not going to change any variables, any fields. Okay, so now we have to return a vector that is formed by like sums of coordinates. So here we like in an older standard of C++, we would have to create a new vector here, and then set its fields here, and then return it. Or we would have to define a constructor that can be like, we would write t vector of like sum of x's and sum of y's. But there is a thing called initializer list class initialization. So we can write as short as return curly bracket x plus q.x. So this x here is going to be this x because everything is happening kind of within our current structure. And after that, it's y plus q.y. Okay. So this is just we have just defined the plus operator, and we can use it. It will work, and it is very short, right? But still, it will save you quite a lot of time and will make code much more concise. Okay, so another operator. What are some other basic stuff? For example, we can go with operator minus, which is basically the same thing, except this formula will have to be different, right? So here we write x minus qx, y minus qy, and everything else is still the same. So I think that this operator, the subtraction of vectors, is actually used more than the operator plus, because this has to do with, for example, relative location of points, and this is just addition of factors. Okay, some other operators that we would like to define. For example, scalar multiplication, which is, for example, we want to double the vector. Well, we can add a vector to itself, but it's like we want to be able to multiply a vector by numbers. So let's write it here. It's not going to be much different. So we still return a vector. So now we want to use operator multiplication. And the second parameter is going to be a number that we are going to multiply by. So let's call it t. So here const, for example. And here we do the same thing. We return this vector initialized by this curly brackets thing, x times t, y times t. Okay, so now we can write some concise expressions with vectors, and this is what we're kind of striving for, that our code will be much more concise and comprehensible, so that it will be nicer to actually write the code. And also, if you will have to search for errors in the code, instead of looking at a very long formulas and combinations of different x's and y's, and you will have to search where you have probably misplaced an x with a y or something, which is, I think, the most common error. Like if you write long formulas and then you have a second one and you make small alterations to that, you usually miss something. So this approach kind of protects you from that. It's just you write simple operators and then you use them every time, so you don't make any mistakes. Okay, so here I use integer type. If your coordinates are like larger, you may go for long here, like the 64-bit integer values. Or if you have doubles, then you just go double here and you go double here, and you're all set. So you have to think it through. And it's also easier, like if you realize that, okay, I'm not good with ints for this problem, I have to go with doubles, it's basically just changing it here instead of changing it throughout the whole code. Okay? So this is very simple. It's an illustration of the principle. Okay, basically every like simple operation we're going to use either an operator or an external function for that. Okay, so let's move on, and these are not the only operations we are going to use for our vectors. So we sometimes we need to know what's the relative position of like several vectors, like what is the angle between them, what is one vector like to the left of another vector, and so on. And like if you don't know the correct way to do that, you may come up with all sorts of crazy formulas. But in fact, we just need two more operations to kind of acquire a lot of power about locating relative position of vectors. So the first operation is the so-called dot product. Okay, so this is probably like some of you may know what a dot product of the vectors is from high school. So the dot product of two vectors, by definition. So we have these two vectors. We have like some angle between them, like the angle that's formed by these two lines, two segments. So the dot product, which is usually written P dot Q, is defined as the length of the product of length of these vectors times the cosine of the angle here. Okay, this is the definition, and we are not going to calculate it this way because there is a very simple formula. So, for example, if the vector P has coordinates xy, x1, y1, and Q has coordinates x2, y2, then what this is actually equal to is x1 times x2 plus y1 times y2. Okay? So this is really easy to compute, right? If we know the coordinates of the vectors. And like, I'm not going to prove this equation. It's not too hard to prove. But let's just think about the implications. Like, what information can we gain just by looking at this number? Okay? So, for example, let's suppose that we have computed this using this formula, and it turned out to be 0. Okay? It just so happens that it's 0. Can we make some implications about that? I mean, let's also assume that P and Q are not 0 vectors, so at least one coordinate is not 0 in each vector. So if this is 0, right, then this product is also 0. So we know that this is not 0. We know that this is not 0. So the product is still 0, so this must be 0. Okay? So we have that the cosine of this angle is 0. And based on that, what can we say about the actual angle? Not quite. Yes, so the angle alpha is going to be, well, depending on the relative location, it can be either like, well, it's okay, its value is 90 degrees. Okay, so if we have this equation here, that means that two vectors that we have are orthogonal. Okay, so if you want to check if two vectors are orthogonal, then all you have to do is to compute this and then compare it to 0. Okay? All right, so what happens if we have the dot product greater than 0? So again, actually this is larger than 0 and this is larger than 0. So if the product is larger, then this is larger as well. So we have a cosine greater than 0. And what does that imply about the angle? If you only know that the cosine is positive. Yes, the angle is less than 90 degrees. Okay? So the picture you want to think about here is this trigonometrical circle, which is like here is 0, here is 90 degrees. And the cosine is like we mark the angle, we have this point here, and the cosine is the length of this projection here. Okay, so if it's positive, then we are to the right of this vertical line, so we are in this half circle here. And it could be that we are under the line, but we kind of don't care because cosine is an even function. So cosine of an angle is equal to the cosine of the negative angle. So okay, this is how we know that if we want to check that the vectors are kind of point to the same direction, then this is how we check it. And if it's less than 0, then we are to the left of this line. So we know that the angle is larger, larger than 90 degrees. Okay, so this allows us to have quite a lot of information. It's not complete information, but it's still quite good. So okay, so some other properties of the dot product which are kind of convenient is that we can prove that this has, well, obviously this is a like commutative function. So P times Q is equal to Q times P, because basically you just exchange, well, the angle stays the same, right? And the length also stays the same. Okay, so we can also see that this is a distributive function. So if we have A times B plus C, where here we have a dot product, then it's A dot B plus A dot C. We can prove that. It may be not quite apparent, or maybe it is from this formula, but okay. Anyway, it's just nice to know that it comes in handy in some cases. Also, using this, we can kind of reinvent the Pythagoras formula for, like, in our case, we are going to interpret it as the length of the vector. So suppose that we just want to know, like, the real number, the length of the vector. So how do we find that? We still want to use this. So if we want to know the length of the vector P, then let's see at what P dot P is equal to. And, well, obviously we have the square of the length. And also we have cosine of an angle which is actually 0, because the 0 angle is the angle between a vector and itself. All right. So the cosine of the 0 angle is 1. So we have just this equation. Okay. So it follows that the length of the vector is the square root of the dot product of the vector with itself. And if we actually substitute that, we arrive at our familiar formula, square root of x squared plus y squared, right? This is the Pythagoras theorem, basically. Okay, so this is our first primitive function, and of course, since this is very basic stuff, we are going to have an operator or a function for that. So how does this function look like? So we can define it as operator multiplication. Again, this is okay to have two multiplication operators as long as they have different parameters. So it returns some kind of number, since, okay, this is number. And here we have another vector, q. And then here we return the number that's computed in accordance to that formula. Okay, so now we are like empowered to use our dot product in the program without abstracting our code too much. Okay, so this was the first thing, the first basic operation, and then kind of complementing to that, we have the cross product. So this is now the operation on a pair of vectors that returns a number. So again, we have the vectors, and we have an angle, but now we actually have to care about the direction of the angle, which means like, so in this situation, if we go from P to Q along like the shortest arc, then we have to rotate counterclockwise, okay? So the counterclockwise rotation will correspond to positive angles, and if Q was located somewhere here, then we would have to go in the other direction, so this is negative angle. Okay? So the direction, we didn't talk about that before, because for computing the dot product, it doesn't matter, as I've said, like the direction of the angle doesn't matter for cosine, but it matters for the cross product that we're about to define. So the cross product is usually written like this, P cross Q, and the formula for that is the length of P times the length of Q times the sine of the angle. Okay? So here you can see that sine takes the sine of the angle into account. So if we, for example, if we exchange P and Q in this formula, then the sine will become like the opposite number. So we can see that the cross product will change its sign to the opposite. Okay. So once again, this formula is not particularly useful for the computation. So the formula to compute this using coordinates is x1 times y2 minus x2 times y1. So this is a bit more complicated than the dot product, because you kind of have to remember which summand is positive and which summand is negative. So the thing to remember that a useful way is actually this can be represented as a determinant of the following matrix. So some of you probably know how determinant works, right? For 2 by 2 matrices, it's the product of these numbers on the main diagonal minus numbers on this diagonal, the product of the numbers here. Even if you don't, you may still remember that you write the numbers in this kind of logical order, and then if we go like to the bottom right, then it corresponds to positive to the positive summand, a summand with plus, and in other direction it's minus. Okay. So once again, let's see what kind of information do we gain from, for example, if we have the value of this number. Okay, so let's see what happens if P times Q is equal to 0. What kind of information do we gain from that? So again, this is positive. This is positive. So if this is 0, then the sign must be 0, right? Okay. So which angles do you sign equal to 0? Yes, it's 0 and 180. Okay. Sometimes if you commonly the angles are measured in radians, so 180 degrees corresponds to pi. Okay, and if you want to use some trigonometrical functions inside your program, then you will have to measure your angles in radians. So here we have 0, we have 180 degrees, which is equal to pi radians. Here we have pi over 2. Here we have, for example, 3 pi over 2, and so on. And we can see that after 2 pi we come back to 0, so it's basically the same vector, and like the cosine and the sine are the same. So looking at the picture, if sine is 0, it happens only at these 2 points. Okay, so alpha is either 0 or pi, and that corresponds to the case where if we draw these vectors like p and q, and we kind of draw them starting from the origin here. So this happens in 2 cases. If p and q are kind of looking in the same direction, so they are co-directed, or they're looking in the opposite direction. So these 2 cases are covered by the fact that they lie on the common line here. So this vector are called collinear. And well, that's that. Okay, so assume that this case happens, and let's think about how do we actually differentiate between the cases when P and Q are looking in the same direction or they are looking in the opposite directions. How would you check it? Yes, exactly. So the actual power comes from the fact that we can use both dot product and cross product, and that defines uniquely the relative position of the vectors. So if we have this case and the dot product is positive, then it must mean this case is eliminated. So it must mean that the angle is 0 and the vectors are co-directed. And if it's less than 0, then the angle must be pi. So they are oppositely directed. Okay, so having both of these numbers provides us a lot of information, and it comes in handy quite a lot. Okay, so here what happens is if the cross product is positive, what do we say? What do we say about that? How can we describe the case? Basically, in this circle, we are located about the horizontal axis. So I will write that A belongs to the interval from 0 to pi. What's the useful description for that? The description is that if we have the vector p and we have the vector q, and we want to rotate from the vector p to the vector q using the shorter angle, like we have 2 ways to do that, but we use the shorter angle, then when this is positive, the direction of the rotation is going to be counterclockwise. Okay, so this is regardless of how vector p is directed. It could be pointing to the left, and we would still rotate it to the vector q counterclockwise. And the opposite situation is when we have this less than 0, then alpha is kind of, I will write from minus p to 0, so the rotation goes the other way. Okay. So let's let's speak a bit more about that product actually. What's the another useful way to think about the cross product? Well, again, it has the property of being it's not commutative anymore, like because when we exchange the vectors, then it becomes like the negative of itself, because the sign changes to the opposite. It is still distributive, so we still have the identity that A cross B plus C is equal to I cross B plus A cross C. And another useful thing to know is that if you look at this formula, you can it may remind you of something. For example, the formula for the area of the triangle, right? Which is basically to make it into the formula for the area of a triangle, we have to put 1/2 here, and then it's basically the same, right? The product of the sides times the sine of an angle between the sides. So here we don't have 1/2, and the interpretation in terms of, we can give it an interpretation in terms of area, and the interpretation in terms of area would be if we have two vectors, then we construct a parallelogram here, right? Using these two vectors, and this quantity here is equal to the area of this parallelogram when the rotation occurs, like when it goes counterclockwise. If it goes clockwise, then this quantity is equal to minus the area of the parallelogram. So this is usually called like directed area, because it has to do with the direction of rotation between these sides. Yeah, so if you want to count some areas, then this formula is actually your friend. And if you want to count the area of the triangle, then you just divide it in half, which you can kind of see if you draw this diagonal, then exactly the triangle occurs, and it's exactly the half of the parallelogram. All right? Okay, so the dot product and the cross product. Do you have any questions at this point about the basic operations? Again, we want to introduce another operator to compute the cross product. We kind of can't use multiplication for both of them, so you will have to come up with a, I don't know, different symbol. Yeah. So you want to return the vector here, or do you want to define two different operators based on this return value, and then to differentiate? I would say that's to like if you actually try to write code this way, I think you'll find it very inconvenient, and also you may not be able to do that because the operators, like the functions with the same name, the compiler does not like it if they have the same list of arguments here and only have different return types, because sometimes he can't quite guess just by the return type what kind of function are you using. So you may want to use some other kind of operator. You may use operator this head thing, for example. You may use some people use and here for some reason. It's basically your choice here. Yeah.
How to using complex to represent the vector. I don't think in fast Fourier transformation.
Okay, I think I'm not going to go into fast Fourier transform right now on the geometry lecture. I will be happy to discuss that with you sometime after. And you can actually use complex because there is a standard complex number class in in the standard library. And also, it just so happens that, well, it has two fields, like real part and imaginary part, and the product of these two numbers has it returns to it returns number with the real part equal to almost the scalar product, and the imaginary part equal to almost cross product up to some signs. But well, I know some people do that, but I find it more convenient and consistent and harder to make a mistake if you just write these functions every time. It may seem like additional work writing this, defining the class and then writing like 5 of this function or even more. But if you get consistent with that, you will get comfortable, and the rest of the code will be just so much shorter. And the thing is, when you have a certain topic that you find hard to implement, the thing is you just have to find a convenient and consistent way for you to write most of the code that you usually use, and then it will not seem like a nuisance anymore. So if you write this like 10 times, 20 times, it will not seem as hard as before. Okay. So let's solve a couple of exercise problems using this dot product and cross product. So the first problem, it happens a lot in geometry that we have to find distances between different objects. So we know how to find the distance between 2 points, right? Because basically, if we have 2 points, then we can. Okay, I think this marker is done. Let me use another one. Can you see anything if I use this marker? Not really. No. Okay. Well, we have a lot to try. Let's see here. Okay, this is much better. So if we have 2 points P and Q, we can, if we interpret them in vectors, then we have this vector, for example, Q minus P, and then we know how to find its length. Okay? So this is convenient. What are other distances that we can try and find? So let's try and find the distance from the segment that's determined by its endpoints, so that's just 2 points, and also a third point R. So we want to find the shortest distance from this single point to the segment. And well, it may seem like kind of a hard problem, because the shortest distance can occur in several ways, right? So if the point is located here, then it's just the length of the perpendicular, and if the point is located here, then it's the distance to the point P. Okay, so there are actually 2 cases, right? The length of the perpendicular and the distance to the point P. Okay, so let's try and write the full code for that, or at least a pseudocode. Okay. So first of all, we have to differentiate between these 2 situations, right? Can we use our knowledge of operations to actually differentiate between that? So. Well, okay, yeah. If you think about it, then like what is the region where the point R could lie, so that the answer is actually the length of the perpendicular. And we can see that the region is like an infinite strip, which is formed by these two lines going through P and through Q, and they are orthogonal to the segment, right? So if the point happens somewhere inside here, then it's perpendicular, otherwise it's the distance to one of the points. All right? So, okay, how do we check if the point R is actually inside this strip? Well, you could do that, but we want to deal with all kinds of situations when the segment goes like this, and then the strip would be like not parallel. Yeah, okay, so the thing is, we want to come up with as simple solution as possible just by using our operations. Okay, so there, like you may have a lot of you may think about it for time, but the simple solution is that the criterion to be inside this strip is like, okay, so consider this angle, right? So between PR and PQ. So we will be to the correct side of this line if this angle is less than, well, at most 90 degrees. Okay? And this thing we can check with what? What should we compute? Yes, dot product, and we check that it's at least 0. Okay, and we have to do that. And we have to do it here as well. So this should be at most 90 degrees. So to check that we are inside the strip, we just have to compute two dot products and compare them with 0. So let's try and write the code. I just want to show that it's going to be very concise. So we have two conditions here. So we have to have R minus P dot product Q minus P at least 0, and also in the other direction, right? So R minus Q times P minus Q is at least 0. Okay, so you can see here that we that our operations on vectors make our code very simple, because every single one of these operations corresponds to some manipulations of numbers. And if you try and write down these operations without using that, you can see that the formulas will be much longer. Okay, so this is the upside of this approach. So here we do something, and otherwise we do basically something else. Okay, so the easier answer is obtained is actually in the other case, because we know that if we are outside of the strip, then the answer is just the distance, the closest distance to one of the endpoints, correct? So here we just return minimum of basically of two the smallest of lengths of this vector and lengths of this vector, and that's the answer. You can, if you're going to use the length of vectors a lot, and well, sometimes you do, you may want to define another operator that computes the length of the vector, and I usually use the unary operator, which goes something like double operator this tilde thing, I think. So it doesn't take any parameters except that it is defined inside the vector, and here you return the square root of the dot product of the vector with itself. And so here you may may write down the formula, or you may want to reuse the dot product that you already have. But like, how do you use the vector itself in an operator if you're inside this? So a kind of clunky way to do that would be to write star this times star this. This is an ugly code, but I sometimes use it. So this is defined to be a pointer to the location of the structure that we are kind of inside in, and this corresponds to evaluating this pointer, and then we just plug it in. So this function computes the length of the vector. Or you may want just to write square root of x times x plus y times y. Or you can use another nice function, which is actually slightly better. It's called hypot, and it just takes x and y. So this function returns exactly what we want to compute here, and it's in some cases it's better to use this because it treats precision errors better. So the thing is, if you're going to use doubles, then you're going to have some precision, some small precision errors. So this function handles this a little bit better, and it's also shorter. So, well, whatever you want, whatever you like. So here we return the smallest of the lengths of r minus p, or the length of r minus q. Okay. So it may seem kind of weird to use this operator here. You may want to use a method len here, and it will go r minus p dot len, and so on. Okay. So in the other case, we have to compute the length of this perpendicular here, and well, how can we compute the area of the perpendicular? Can we interpret that in terms of our other operations? Yes, exactly. So well, almost. So if we calculate the area of this parallelogram, then another formula for that would be the length of the base here times the length of the perpendicular. So to calculate the length of the perpendicular, we write, so let's compute the area of the parallelogram, which would be q minus p cross r minus p. And then we should divide that by the length of p minus q. Okay? So this is actually almost correct. Can you see the like when this code goes wrong? Yes. So this cross product is it can be negative sometimes, right? So we don't want the directed area when you want the actual area, and to do that we just have to find the absolute value here. So in actual code, it would be a function abs if this is integer, or f abs if it's double. Okay. So you can see that the code is actually like very, very simple, and you can see what's going on just by looking at it, right? So there are no complicated formulas with a lot of coordinates. It basically speaks for itself, right? So we take these vectors and then find their dot product, and then we return this area if you know that this is area and we know that this is length. So it kind of comes together. So you can read it much better than the usual geometry code. Okay, so this is settled. Another exercise problem which I probably won't go in now too much. If you're not going through the second part of the lecture, this may be an exercise for you for the rest of the time. So the problem is if we have two segments defined by their endpoints, so like P1, Q1 and P2, Q2, you have to check if they have a common point, basically. Okay? So again, you can see that there are quite a lot of different cases here. Like there are a lot of ways that this segment can be positioned relative to each other. But again, if you apply the dot product and the cross product in the correct way, and I actually don't think that you have to use the dot product here on the cross product, then you can determine this with relatively few effort. The only thing here is you will have separate cases when the vectors, when the segments are parallel, and when they are non-parallel. Like when they are non-parallel, it's a kind of a simple case, and if they are parallel, then the hardest case, the special case, is when they lie on different lines, or if they lie on the same line. So these are the only cases, but other than that, this problem just shows the power of the basic operations all too well. Because if you were to solve this without knowing these operations, just by coordinate manipulation, you will probably want to kill yourself after a while. So okay, let's go further and speak about some other objects that we usually encounter. So the next object we're going to talk about is the straight line, an infinite straight line. Okay. So when we have two segments, we can define it by 2 points, and when we have a line, we can do the same. Like if we have a line, then we can choose 2 points here and here, 2 different points, and that kind of defines the line uniquely. Okay. The thing is, this is not the most suitable description of a line, because well, let's think about what are the other ways to define a line. So, for example, instead of this, you can have a vector and you can have a single point and then a direction vector for the line, and that also defines the line uniquely. But also, let's think about how do we. So, assuming that we have this point P and the vector D, the direction vector, let's think about how do we check if another point lies on the same line. Okay, so we have another point Q, which is now not on the line. Well, it could be, but it's a separate point. So how do we check if this point actually lies on the line? Yes, so basically we want to check if the angle is 0 or pi, and that's exactly what our cross product does, right? So we have something like Q minus P cross product D is equal to 0. And if we expand that and we write xy here, and we want to expand this and rewrite this in terms of x and y, then we will see that this becomes x times something. Actually, I think it should be minus x times dy plus y times dx, I think, and also minus p cross d. Okay, so what is this equation in terms of coordinates of the point Q? This is actually a linear equation, right? Because it's something times x and something times d plus basically a constant that doesn't depend on the point is equal to 0. Okay, so we kind of know that by now, but so each line can be defined by a linear equation, and the linear equation is actually better in most cases. So instead of having this, we will define the line by 3 numbers. That is the coefficients of the linear equation. So we are going to use ax plus by, for example, plus c equals 0. So these 3 numbers define the line. Okay. So if your line is given by 2 points as before, and you want to convert to this form here, then you know what to do, right? You have to write this equation and then rewrite it in terms of x and y, and you can see what the coefficients are. Okay. So let's think a little bit about what exactly are the coefficients. What do they represent? Can we give some meaning to them? So, in fact, the a and b are the most important. We will even make a special vector out of them. So the vector denoted n with coordinates a and b. And the special meaning of this vector is that if we have a line defined by this equation, then this vector is orthogonal to the line. Okay, so it points in one of the directions. And if you want to have a vector that goes along the line, then you can take this vector and rotate it by 90 degrees in one of the directions. And for example, one of the vectors that you can obtain is minus BA. So why is this orthogonal? Because if you take the dot product of these and these, you get 0. Okay. But usually, this is the kind of vector that we want to work with, and we can use that to vector to find, for example, the distance from a point to the line very conveniently. So we have already found the distance from a point to a segment defined by 2 endpoints. This is a similar situation. Instead of we don't have a points, we only have these numbers. And the thing is, there is a simple formula. I'm probably not gonna prove it. You can try and prove it yourself. But the thing is, we can see that the distance is 0 when this equation is 0. Okay. These are exactly the points belonging to this line. Okay, and if we go and move in the direction of this normal vector, of the orthogonal vector, then the distance increases, and this value also increases. If you go in the negative direction, then this becomes negative, and the distance still increases. Okay, so let's go with this simpler version of that. How do we determine on which side of the line a point is? The thing is, this line is kind of so on one side of the line we have the points for which this expression is positive, and this is exactly the half plane where this normal vector is pointing to. And on the other side we have the negative ones. So for example, if you want to check if 2 points are on the same side of the line or on different sides of the line, and you can look at the sign of this expression, and if they're the same, then the points are on the same side. Okay? So to compute the distance, we are almost there. We write down this expression. It kind of measures how far from our line the point is. and in which direction do we have to go. So if you take the modular, then it's almost a distance, but we want our expression to be like not to depend on some transformations of these equations that will give us the same line. So for example, if we multiply all of A, B, and C by 2, then it will have the same set of solutions, but this value will increase by 2. So in fact, to find the distance, you go with this formula. You divide over this number. Okay? All right. So once again, the line, the most useful way to define the line is to have this equation. And in the code, you may want to store 3 numbers, but it's usually much more concise to store the normal vector and then the number C. Okay? Because this normal vector is used just so much across the code if you have the line. Okay. So another classical problem that occurs a whole lot in geometrical problems is the intersection of 2 lines. And there are a lot of ways to approach the problem. For example, depending on which way do you represent the lines. But if you have the representation with the equations, then what you have is basically a system of linear equations. And we kind of know how to solve these ones, right? We can do that by elimination. We can do it by a lot of different ways. So if you have to do that, and you like if you do it every time, like if you solve these by hand, then there is a neat rule to solve the system of linear equations called Cramer's rule. So we can actually write down the solution for this. So for x, we will have a ratio of 2 values. Both of these are determinants of 2 by 2 matrices. So here, in the denominator, we will have the determinant of this matrix that just consists of A's and B's in the order they come here. And so to compute, so here the determinant will be almost the same, except that first we want to rewrite this equation as minus C1 and minus C2. Okay, just for these to work. And then what we do for x is we take the column of coefficients that we have relative to x and replace it with the column that corresponds to nothing. Okay, to the right side. So the equation, the determinant here will be minus C2, minus C1 B1 and minus C2 B2. Okay, so this is a rule that's nice to remember, I think, because you have this determinant anywhere, and then you just replace one column with another column.
What's the name of the rule?
It's called Cramer's rule. And it actually works for a system of any size, except for you will have larger determinants here. And for y, we do the same thing. In the denominator, we will have like the same thing, and in the numerator, we will take the same column, but rather replace b's than a's. Okay. So this is just the answer. You can memorize that and use it. So let's see. Sometimes the solution does not exist, right? And the solution will, these formulas will give you nonsense exactly when the denominator is 0. And if you look closely enough, then you can see that this is exactly the cross product of the normal vectors. Right? So these formulas will give you nonsense exactly when the normal vectors are collinear, and that means that the lines are parallel. And that's when you kind of can't have a unique solution. It's either they do not intersect or they coincide completely. And well, and here this can also be interpreted as a cross product of some other vectors. So you can even reuse your code for the cross product to make short work of computing the determinants. So this is the way I usually do that. So this is all about intersecting two lines. And well, if you want to intersect, if you want to find, like we've talked about the problem of intersecting two segments, right? Of checking if they intersect. So to obtain the point of the intersection, we first check if they actually intersect, and then apply this rule to intersect the lines. Or we could intersect the lines and then check if the line actually belongs to both of the segments. Okay, so this is all about the lines. Any questions at this point? Okay, we are kind of out of time, but I'm just going to cover two small things. By the way, during the contest you will have a small cheat sheet, just a piece of paper that has most of the formulas that I used here. So if you missed something or you forgotten the formula, then it's not too bad. Okay. So the other common object is yes, it's just AB, basically. Okay, so the other common object is the circle. And the circle is defined by a point and the radius. Okay? Well, there are actually two different objects that you can call circles. First, the circle is like everything inside this, and the other object is the circumference, which is like only the border of the circle. Okay, thank you. And usually we treat with circumferences, but I will call them circles anyway. Okay, just because it's shorter. Okay, so what are the problems about the circle that you can try and solve? Actually, there are quite a lot of them. For example, you can try and find points of intersection of the circle and a line, which is given, for example, by equation. So how do you solve that? You can go with an algebraic way. You just write down the equation and then you kind of figure out what happens. Another way is more constructive, so that the answer consists of our primitives. So first, we start by finding this distance here. Okay, we know how to do that at this point. And we have the radius. So if the distance is larger than the radius, then obviously we have no points of intersection. Otherwise, we know that we have to find these 2 points. And to find them, we have to take this point here and move to both of the sides by the quantity, the square root of r squared minus d squared. Okay, so one way to do that would be to find the direction vector of the line by the formulas we already know, kind of, and then multiply them by a sufficient number so that the length that we move is exactly the one that we want. Okay. You also have to take care that if you just write minus BA for the direction, it may not have unit length. So to make it unit length, you have to divide this vector basically by its length, and well, we know its length. This is usually called normalizing the vector, basically multiplying it by some positive number, so its length becomes unit. So this is one way to do that. There are some other ways. Probably I won't go into that. Okay. I would have, but I've already been late, and I'm sorry. So let's just discuss a few more problems real quick. We could try and intersect the circles as we had to do on the contest yesterday, right? There are several approaches to that. I want to discuss one in particular because it has some other important things to it. So here we have this. We know that we have this triangle with sides equal to the radiuses of the circles and also the distance between the centers. So, for example, if the distance is greater than the sum of radii, it won't have any points of intersection. Or the other case when they may have no intersection is when one of the circles is inside the other, so that the distance is smaller than the absolute difference between the radii, so that the triangle inequality is violated. And basically, after we have this triangle, we have enough information to figure, for example, all the angles, right? So we can find, for example, this angle here by applying something called the cosine theorem, which says that R2 squared is equal to R1 squared plus D squared minus 2 R1 D cosine. So out of this we can figure out the cosine here, and we can also figure out we can almost figure out the sine of the same angle, except for if you write down the sine, then it has to be square root of 1 minus cosine squared, except that we don't know the sine here. Okay, and taking two different sines here will actually correspond to two different points of intersection. Okay, so the only thing that we have to do now is to take, for example, this vector here and rotate it by a certain angle, if we know the cosine and the sine. And it may sound like a complex problem, but the formulas are actually very simple. If we want to take a vector with coordinates x and y and rotate it by the angle alpha, then the resultant vector would be x cosine alpha. I want to say minus here, y sine alpha. Then here we have x sine alpha, and here something along the lines of plus y cosine alpha. I may have messed up the signs, but anyway, you will have this formula in the handout. So this is just the idea. Okay. So if we have this, then we just rotate this vector so that it aligns with the point, and then we change the length of the vector so that it becomes exactly R1. Okay. So this is like the interplay of a lot of different things we can do with vectors and points and angles. And we can do quite a lot and solve a lot of problems. Again, as an exercise, you can apply the same almost trigonometrical approach to solve the problem of constructing tangents from a certain point to a certain circle. Okay, it's basically the same. You have to use the fact that the tangents are orthogonal to the radii at the corresponding point, and then you have these triangles, and then it's basically all you need. Again, you may try it and work it out for yourself. Okay. Any questions? So the last thing is one of the I guess one of the most important geometrical algorithms, which is constructing the convex hull of a set of points, which is it feels more like a real problem where we have to process a lot of data, like 100,000 points, where instead of when we just have to think about two lines and think about how they intersect. So the problem is about if we have n points in the plane, we want to construct like the smallest region that smallest convex region that contains all the points. So something like this. It's going to be a polygon. It's going to be a convex polygon. And by convex, I mean that if we travel along its border in counterclockwise direction, then we always turn left. We never turn right. There is a more like mathy definition of convex, but that's basically enough for us. Okay, so if we have these points, how do we construct the convex hull? What would be the most basic approach to constructing the convex hull? The most basic approach would be to try and figure out which pairs of points correspond to the actual sides of the convex hull. Okay, so what's the difference between this pair of points, for example, and I don't know, this pair of points? So for the second pair of points, if we draw a line here, then it actually cuts our set of points in two halves, right? There are points on one side and there are points on the other side. But here, if we have the side, then all points basically lie to the left. And that's the difference. So one approach, the simplest approach, would be to check all pairs of points, and then check if everything else lies to the left of this line. And how do we check if it lies to the left of the line? We basically, we have the cross product, right? So we have to check the direction of these rotations. This is not the most effective algorithm, of course, and the algorithm that we are going to use is the so-called Graham algorithm. It's actually quite simple. It's fast to describe, which is why I have started it now. So it starts with, let's try and locate at least one point that belongs to the convex hull for sure. And that would be the leftmost point here. And if there are several leftmost points, then, for example, like several points on top of each other here, then we want to take, for example, the lowest one. Okay, so one point that belongs for sure, like you also may want to think about what happens if a point belongs to the side of the convex hull. And usually we say that it's not vertex, but you have to be careful about how to actually treat these points. And I will talk about that in a moment. So we have located this very important point. And so what do we do next? The next thing that we do is let's try and look at everything else from the viewpoint of this point. Let's call it O. So if we like rotate our line of view from left to right, the points will come up in certain order. Okay. And what we want to do is we want to sort all our points with respect to this order. And it may sound hard, but we've actually got everything that we need to do. So first of all, we are not going to write this sort by ourselves. We are going to use the standard C++ function that takes the pointers or iterators to the start of the list, for example, a begin. If you have a vector and a end, and usually that's all. If you want to sort numbers, then that's all you need. But here we have to. It's slightly difficult to describe what we actually by which criterion you actually want to sort these points. So the sort procedure actually takes a third parameter, the function or something that can compare points, can compare objects, so that it will be used instead of the usual comparison for these objects. So, for example, we may want to write a comparator here. So, in our case, let's talk about what the comparator is going to be. Usually, in this case, I recommend to define a special structure called, well, we have called it comparator. So why a structure? Because it will have, okay, a vector. I did say vector. So it will store this point O here, and then so we initialize this with our origin point O, and then we define the operator that will actually be used here. And this is going to be operator not less, but the operator square round brackets, which takes two vectors, A and B, and then compares them with respect to the point O. So it should return true if the point A should come before the point B. And inside of that, it will have a very simple thing. It will compare this cross product 0. So the reason why it actually works is because of the way we have chosen our point O. So we know that all other points lie in the same half plane with respect to O, like this. So this will actually work as a comparator for our sort function here. But if it's not the case, and if the point O could be, for example, here, then what would happen if you try to use this comparator is your sort procedure would malfunction, and your program would likely just break and abort and would not work at all. This has to do with the fact that there are some comparison violations if you try to use this operator for sorting the points around this one. But if they're all in the same half plane, that it works like a charm. So we don't care for that. So this is the way how we sort our points. We define the comparator, and here we are going to write something along the lines of comparator of O, because it has to be initialized with the point here. So after that, we are going to process our points in this order, and at every stage we are going to have the convex hull of the first few points in our order. So the only thing we have to do is to consider the next point in the order and see what how our convex hull change. Well, obviously it's going to be a new vertex here, but now if we try to extend our previous convex hull here, you can see that this is the wrong turn, right? So we turn in the wrong direction, so this is not a convex polygon anymore. So what do we have to do is we have to erase this point from our convex hull. So now that we have done that, it's fine. And how do we check for that? How do we check that this point is bad? Basically, we have to see what's the direction of the rotation, what's the directed angle between the certain vectors. So this vector and this vector, and we know the cross product, and well, we know everything that we need at this point. It may happen that the next point is also bad, so we may have to erase that as well. And we do that by while the last point out of the previous points it becomes good. And at this point we say that, well, okay, then we insert the next point and we are done. So this is the new convex hull. So you can see that how do we store these points in the convex hull? So you can see that we have to append new points from time to time, and we also have to erase the last point in our sequence. So the data structure that we want to use is called stack. Okay. Or for example, you can go with vectors, since you can push back and pull back and pop back. And so that's basically all of the algorithm, and it constructs convex hull in the end. Let's think about the complexity of this algorithm for the last part. So first we have to sort the points. So that takes n log n time, as we know. And then we have to do this stack thing, right? And you can see that each particular step can take up to like linear time, because we can have like this convex hull, well, I know, something like that, and then we have these points, so we should erase basically everything that we have constructed. So it may take a lot of operations here, but in total it will be linear time. Why is it going to be linear time? Because well, let's consider any particular point, right? So at some stage it will get into the convex hull, and probably it will get erased at some stage, but it can only get erased at most once, right? So the total number of deletions from our convex hull is at most the number of points, despite the fact that they all can happen on the same stage. So this takes linear time, and that's it. After that you have the convex hull, a convex polygon, and that's pretty good. That's pretty useful for some problems. Usually the hard problems go first construct the convex hull and then solve another hard problem. Okay.
Why did you choose to the ground?
Like when you go from left to right?
Yeah.
Yeah, you can do that. I mean, they're not too much different. So another approach I'll just quickly mention is that you can sort the points basically by x coordinate from left to right, and then you construct the upper part of the convex hull and the lower part of the convex hull separately. So they comprise the convex hull. And how do you do that? Basically, you maintain a stack again, and then after you consider the new points, then you have to erase everything that has a wrong turn at the end. So I guess it simpler in some aspects. For example, you don't have to care a lot about the comparator because the sorting procedure is very simple. Okay, and after that, it's pretty much the same. There are not too many differences. So you may want to use this approach if you want, or you may want to go with Graham's algorithm. It's up to you choice. Okay. Any more questions about anything we've covered? Okay. So I think that's it for the basic part of our geometry. And now I think we're going to have a short break, like 5 minutes. And then we'll come back here and discuss some more complex algorithms. Okay, thank you. We're good? Okay. So, let's talk about more complex problems that you can encounter. Well, it's rather they are rather approaches and like standard problems. You will rather not encounter them per se, but there are still approaches that are important, if you want to solve complex problems in geometry. So the first problem we're going to discuss is that assume that you have a set of points in the plane, a lot of them, like 100,000, and you want to find a pair of points that are at the largest distance among all possible pairs. Okay, so for example, probably this one. This pair is also called the diameter. So just to get an idea, how many people know how to solve this problem faster than n squared time? Okay, so let's discuss the solution. So obviously there's an n squared time solution where you can try all pairs of points, right, and choose the one at the largest distance. Let's try and speed it up. So the first thing that we're going to mention is this pair of points should belong to the convex hull. So out of all optimal solution, there's one where both points are vertices of the convex hull. Okay, we can prove it. It's not too hard. So assume that we have like one point anywhere and another point strictly inside the convex hull. Okay, so we have this segment, and let's draw a line through this point here, orthogonal to the segment. So if this point is strictly inside the convex hull, then we can see that there is at least one point, at least one vertex of the convex hull on the other side of this line. Okay, because if there are no points, then we are on the border of the convex hull. And if we take this vertex, we can see that since it's on the other side, then this distance is actually larger. So we should only care about the points on the convex hull. All right. So now we have the convex hull. We kind of know how to construct it. And what now? We still could have basically all of the points on the border of the convex hull. So how do we speed our computation up? The wrong solution would be to take a point and then argue this way. Okay, well, it seems that if I start here at this point and move counterclockwise, then it kind of seems that the distance from this point to the other point
increases up to some point and then it decreases, right? So if this is the case, then what I would want to do is to apply the two pointers approach, where you start with this point and then you move this point further until the distance increases. So this is the farthest point from our previous one. Then you move this point here and try to move this one further until the distance increases, and so on. So this would ideally be an n log n solution, because we need n log n for constructing the convex hull. The only problem is that it doesn't work. It's almost correct. It's so close to being correct. The thing is, if you consider the distance between the points themselves, then it can be not monotonous, even in the convex polygon. The simplest example is that assume that we have a single point here, and we draw a circle of a certain radius, and then we add some points very close to this circle, but moving in and out of the circle. So here it turned out not to be complex, but if you space them a lot, if you space the points a lot and they are close enough to the circle, then the polygon will still be convex, but you can see that the distance is kind of increases and decreases and does whatever. So this approach is so close to being correct. The only thing that you have to change here is, instead of counting the distance between the points themselves, so we were trying to locate the farthest point from this one, and instead of that we will do another thing, and instead of that we will choose a side of the polygon and we'll try to locate another point that is the farthest from this side. Okay, so from this line, actually, from the line containing the side. And you can see that from convexity there now can be no mistake, because we move away up to some degree, and then when we move back, the distance to this line is bound to decrease. Okay, so now at least we have the monotonicity, and now the two pointers approach will actually work. The question is, what does this do with the original problem? Because originally we wanted to find a closest pair of points, but here we are finding the distance from a point to a line that is not even a side. It's a line containing a side. The point is, after we have found this farthest point from a side, we check two candidates for the farthest pair of points, and these are basically the farthest points and also end points of the side. Okay, and we claim that if for every side we find the farthest point and check the candidates, the farthest point and the end points, we will find the correct answer. We will find the farthest pair of points. The reason for that is that basically, if you consider our convex hull and there is a farthest pair of points, okay, so they are at certain distance, which is the farthest. Let's draw two straight lines through these points, perpendicular to the segment, and after that, what we want to do is rotate these lines gradually while these lines go through these endpoints of the segment. Okay, so let's try and imagine what happens. After some point, one of these lines will begin to intersect the polygon, right? So this is almost like a physical process. We have this object and we have clamped it with some kind of fixator, and then we try to rotate them, and then at some point we have an obstruction. So let's look at the first moment when we have an obstruction. So we have two lines here. These sides turned out to be parallel, but let's fix that. So this side will go over here. Okay. So what do we have here? One of the lines will contain a side, one of the sides, because that's the obstruction, and the other one is still going through another point from our original pair of farthest point, right? So you can see here that this picture implies that this point has the largest distance from this line. Okay, because all other points are contained in this strip of parallel lines. So if another point had larger distance from this line, it would have to be outside of the strip. Okay. So this means that for this particular pair of farthest points, we will find the answer when we consider this side, okay, the line containing this side, and we will be bound to find this point at the farthest from the line, and that's how we find the answer. Okay. Are there any questions about this algorithm in general? Why something works? How to actually do that? So, yeah, from the implementation point of view, it's basically you just construct a convex hull, and then you apply the two pointers approach, except the points here are looped. So when you move the side and you move the point forward, you may have to travel through like the 0th point, and you have to take care of that. Otherwise, this part, after constructing the convex hull, works in linear time, because as our side travels around, like so, what happens to this point? So it may stay in place. It may travel forward a few places. It may travel forward a lot, but it never goes back. And it's pretty clear that as this side moves along the polygon once, then the farthest point will also move around the polygon once. It cannot be the case that it just travels, 5 times, because, well, it doesn't make a lot of sense. So, and a part of that, we only have some constant time computations, like computing the distance from the line to the point, and basically that's it. In fact, if you you don't have to consider the distance itself, okay? Because the distance from a point to the line is a real number, and the thing is, you want to avoid real numbers as much as possible in your program, in the geometry, because when you have real numbers, you have precision errors that are bound to happen, and if you have to compare some real numbers, you have to be really careful to compare them, since you should allow some room for the precision error. Like basically, if you have to check A equals B, then real numbers are almost never equal because of very small precision errors. So instead of that, you have to check that their difference has small absolute value, and that is usually A minus B is equal some very small epsilon, which is 10 to the, I don't know, 10 to the minus 7th, 10 to the minus 10th. It is pretty hard to guess what this epsilon should be. There are some ways to estimate that, but there's really no consistent way of telling that. Well, okay, there are kind of there are ways. So, for example, let's think about the problem of intersecting two lines, right? And the thing is, whenever you have the number, you want to estimate what is the what is the distance to the actual closest number, right? So we know that the intersection point here is a quotient. Its coordinates are quotient of two integers, so a over b, and we know that b is a determinant of a certain matrix, which coordinates are coefficients of the lines, right? So if the lines have 10 have coefficients up to 10 to the 9th, then b should be up to 10 to the 15th. And you have something here. So usually if you have a quotient of two integers, then the precision error that you can make here is about 1 over the denominator. Okay, so if you have these kinds of numbers and you want to compare them really precisely, then your epsilon should be 10 to the minus 15th or 10 to the minus 19th, something like that. So there are ways, but in general it's very hard to estimate. You can also increase your precision by using some more precise floating point types. So you almost never want to use float. You almost never want to use float because it's too imprecise. It's so imprecise. It's curious. So double is the usual one. You may want to use long double. It has slightly more precision. Long double only exists in G++. If you use the Microsoft Visual Studio compiler, then long double is actually the same as double. So if you have troubles with precision, you may want to change double for long double. Where was I? Okay, so the precision rant is over. So about this algorithm, I was talking about the fact that you don't want to use real numbers, and in this problem you don't have to, as long as the coordinates of your points are integer, because you don't actually have to compare the distances, right? In fact, instead of comparing distances, you can compare the cross products of this vector and then this vector, okay? Because in fact this cross product is exactly the distance multiplied by the length of this vector, but since this length is the same while we are moving the pointer for a particular side, then it doesn't matter, and the comparison will be the same. But the cross product is an integer, so it will be much nicer. Okay, so this is the problem of finding the diameter. Any more concerns about what could go wrong here? Yeah.
When you start with your 2 lines,
Oh yeah.
one on one side.
Okay.
How do you decide which one is the next line intersecting the body?
Okay. Look, we don't actually need to rotate both lines simultaneously. We only use that to prove a point that our algorithm works. So the algorithm that you are describing is also correct, because so the other approach is to basically do this thing over and over again. So When we rotate these lines, one of them encounters a point, and then instead of rotating it about this point, we rotate it around this point. So it's called rotating calipers because of like this thing that kind of clamp the polygon. And it also works. But here we do something different, which also works. Okay, so this is just 2 pointers where we kind of have one caliper here that moves around the sides, and the other pointer just points to a single point, and we only move it forward until this distance increases, right? So it's like here, okay, if I move forward, it increases, and then it increases, and then, oh, okay, it decreases, so we must have found the maximum. And then when we go to the next line, to the next side, we start from the same point and move it forward. So it's kind of a different flavor of an algorithm, but it's really almost the same. Okay. Yeah. Mm-hmm. Oh, I'm sorry. Yeah, so if 2 sides of the polygon are equal, so when this happens, you will arrive at which point? Probably this. So, in fact, I think it does not matter, because the reason for that is that assume that you take this point, and in fact the farthest pair is like this one. So we kind of missed. But in fact, if we go to the next side, then here we will be bound to take this point, even there's a parallel side, because if we take the first point consistently, then we will take it every time. So if we didn't find maximum here, we will find it on the next iteration. And the same thing goes like for the other case. So you just write here you move forward until the distance either increases or does not decrease. There are 2 different solutions, and both of them work. Is my point, basically. So you don't have to care about that too much. Okay, any more questions? That was a good question, by the way. Okay, so let's solve kind of an opposite problem, and instead of finding a pair of the most distant point, we will find a pair of the closest points in a set of points. So I'm just curious, do still a lot of people know how to solve it? Yeah, quite a lot. Okay. So here you can see that now we have nothing to do with the convex hull, right? Because the closest points may be inside, and like convex hull does not have anything to do with that. So we will not use it. Okay, again we have the n² approach, but we want to improve on that. The optimization here comes from the approach called divide and conquer. Oh, okay. So the optimization is as follows, basically. Assume that we have a set of points, and we've divided the set into 2 parts in some way. For example, we have drawn a vertical line. And we have found the best answer for both of these halves, basically with a recursive algorithm. So we assume it works. So we have found the correct answer here. And we have found the correct answer here. And we know that the current best answer is G. Okay? So the only thing that's left to make our algorithm work is to consider all pairs where one point is from one half, the other point is from the other half, and their distance has a chance to improve on d. Okay? Because like if all of them are larger than d, then d is the answer. It doesn't make sense to consider them. So this is the key optimization. We will extract a lot of speed up from only considering points that have a chance to improve on d. Okay. So let's start with like a general framework. What we are going to do is to, well, as I've said, this is a recursive procedure. But before that, we have to sort our points by x coordinate, and if they're equal, then by y coordinate. So basically, a lexicographical sort. And so then we do this procedure. I'll call it DNC for divide and conquer. So I'm assuming that there's some global array of points, and I want to solve the problem for a certain range of points. Okay. So I'm a fan of approach that whenever you have a range, you want to use a half interval. So in fact, when we are having L and R, we are considering all points with their indices in this set. Okay. It seems kind of more natural to use segments here, so that the right border is included, but it turns out that this is simpler. Okay. In a lot of cases, because formulas are shorter, there are less special cases to consider, and so on. So yeah, I guess our function should return double or something. And okay, so what do we do here is we find the midpoint and then obtain the preliminary answer d as the smallest of the two numbers for two halves. Okay, and okay, now what? So now we have our d, and the number d means that in either half of our set, no pair of points are closer than d. Correct? Okay, because otherwise that would be our answer. So if we have this, if you want to consider pairs that have a chance to improve on d, then basically, if we consider this vertical line that separates two sets, then it doesn't make sense to consider points that are so that their x coordinate differs from the coordinate of this line by more than d. Okay, because surely if they are somewhere here, then all the points on the other side are farther than d from them. Okay, so we kind of want to ignore them. Okay, so this is the first consideration. The second consideration is that in either half, no points are closer than d, and if you think about it, we have a very narrow strip of length d, of width d, and we also have the constraint that no two points are closer than d. So if we try and pack as many points here as possible, it turns out that there will be basically a lot of space between them. So it cannot happen that a lot of them are in a small portion of that. because of the constraint that they have to be at least d apart. Okay, so what we are going to do now is, so we have these kind of packings here, right, inside of this strip. So now our approach would be, for each point here, for example on the left side, we consider all the points on the right side that are inside the strip. So we know that, for example, this is the, like, if this is the y coordinates, then this is the delimiter between the points that are higher and the points that are lower. And what we do now is basically we start from this delimiter and go upwards and basically try to improve the distance d, the global answer, with all the distances of points that we meet here. Okay. Is it clear how it works? So basically, it's a kind of naive solution. So now we have these two lists of points, and we kind of try all pairs of points. So for a particular point, we start here, and here is the the lowest points that is higher than this. So we try this, okay, and then comes, for example, the next point. So we want to try this, and then comes the next point, and we want to try this, and so on. Okay, the only optimization that we're going to use is that if we get too far from this point by y coordinate, so if this distance between points, the vertical distance becomes at least d, then obviously there is no chance of improving anymore. Okay, so we do that, and we do the same thing for all points on the right side, except that we match with the points on the left side. Okay, so let's try and write some code for that, I guess. The thing is, the other thing that I didn't mention is that initially our points are sorted by x coordinate, but here in this stage it is much more convenient to have them sorted by y coordinate. So in addition to finding the answer, our procedure will also sort the points by y coordinate. Okay, so here, after this function is done, it should return the correct answer, and it also should have the points in the corresponding range sorted by y coordinate. And you can see that here it's still done with divide and conquer, so it's very much like sorting with merge sort, which is pretty much the same, right? It does recursively and then it merges something. So this is pretty much what we are going to do here. But first, we are going to use basically two additional lists because it is much more convenient to have these points inside the strip in additional array. Okay, so we have some some arrays called, I don't know, left part something and right part something. You could probably, it's better to make these vectors, but I won't care too much about that. So here we do our merge procedure. So I guess I won't go into a lot of details here. I will just write merge to ranges, and also construct the left part and the right part. Okay, so at the end of this, and the end of this part that I didn't go into, we expect the range to be sorted, and we also expect that these two arrays will contain the points inside the strip on either side by increasing their y coordinate. Okay, so it's easy to do that in parallel with actually merging two ranges. Okay, because naturally you process all the points on either side by increasing of their y coordinate, and if they are close enough, then you just push them to one of the arrays here. Okay, so now we have these two additional arrays, and we have to work with them. And how do we work with them is basically another instance of two pointers. So we know the lowest points here and here. So let's make two variables, two indices that are the indices of the current points we are considering. So basically, it's like merging again. We are looking at the lowest point and we move it forward, and then we look at the next lowest point and then we also move it forward. So it's a lot like merging. So basically, we go while there's something to process. We see. So assume that the point on the left side has lower y coordinate. Okay, so this is something like if the ith point of the left part has y coordinate like less than this stuff, then what happens here is, okay, so we have this here, we have this here. We start from the pointer j and move upwards, and trying to improve on d, unless this point is too far. So that's basically, we have an additional pointer k that initially is equal to j, and we go until well, k is a valid index, so it's like less than right p size if it's a vector, or less than something else. And also the y coordinate of this point should not be too large, so something like right p of k dot y should be less than the y coordinate of this point that we have chosen plus d. Okay, so that's left p of I dot y plus d, and then plus k. Okay, can you read what's written here? Should I read some parts aloud or explain something? Okay, so here what we do inside this cycle is basically we go d is equal to minimum of d, and the distance, I will just write dist, of the left part, the ith point of the left part, and the kth point of the right part, and that's it. So we proceed naively, starting from this upwards until we are not too far. Okay, and here we probably should go like plus e plus I, and then we do the same thing but symmetrically for the case when this point is the lowest, and then we start from the next one and go upwards. So that's basically it. So we merge here, we construct these parts that lie within the strip, and then we do the two pointers with the additional cycle. So let's try and estimate the complexity here. Yeah. The pointer j is modified in another case, which I didn't write, because it's just symmetrical case. Okay, so this is 2 pointers, and in this case we move I and run forward from J. And in other case it's all vice versa, basically. Okay, so let's try and estimate how long does it work. So basically it's a merge sort, as I've mentioned. So it works in n log n. At least these parts of that. Okay, but then there is this part, and even though it's 2 pointers, we have this kind of weird cycle. Okay, so this cycle, if we didn't have the constraint that the points on either side are at least d apart, it could happen that this cycle worked like for linear time every step. But it's quite convenient that we have this constraint. So we claim that on each iteration, this cycle will work only like for a constant amount of iterations. And the reason for that is that, let's see, so we only have the chance on each step, we only have the chance to process the points that belong to the square, because like the intersection of the strip, and also we don't move too far on the y coordinate. Okay, so the square is d by d, and we also have to fit. So how many points can be inside the square, provided that they are at least d apart. You can see that not much, probably. So you can place probably 4. I don't know if you can place more than 4. Probably not. But anyway, despite the fact that this cycle kind of does not have a limit on the number of iterations, it is still bound to work for only constant amount of iterations because of all the meaning D has and the way we do things. Okay, so assuming that this works in constant amount of time every iteration, then basically all of these works in linear time, and then by the standard, by the same reasoning that we estimate the working time of merge sort, we have that this works in n log n time. Okay, so this is the solution. Are there any questions about that? Some concerns? In fact, you don't even have to use double here, because if your points have integer coordinates, then instead of distance, you may optimize the square of distance and its integer. Okay, so let's check the time here. Ooh, okay, so I'll probably cover a few more things. Okay, so another type of problems that you encounter, I think, quite frequently are the query points, the query problems, where you have some geometrical objects and you have to perform some queries in them. So a good example, like a very basic problem, is you have a set of points, again, n points in the plane, and you get the query. You have to process a lot of queries, where a query is a vector, so xy or ab, and you have to, among all points, you have to find the maximum of the value ax plus by. Okay. So this is like the dot product, right? And well, we want to go faster than just check all points, And we know that since this is a scalar product, a dot product, then the point that will have the maximum value is going to be the point that is as far in this direction as possible. Okay, so basically the point that's going to be an answer is the point so that if we draw a line orthogonal to AB, then everything else will going to be on this side. Okay, because basically going forward increases the value of the dot product, and when we go back against the direction of the vector, it decreases. Okay, so that gives us some ideas. First of all, again, we don't need to consider any points other than the vertices of the convex hull. So here we construct the convex hull before we even do anything. And then we have to process these queries. And there are two types of problems that you can consider. There are offline problems and online problems. In the offline type of query problems, you can read all the queries beforehand and do some, like, process them in a bunch. Usually you can come up with simpler solution, but let's consider an online version. So we can't read all the queries and then preprocess them. Rather, when we get the query, we'll have to answer it right away before we get the next one. Okay, so we have the convex hull. Now what? So we have a certain vector, so AB, and we want to find the vertex of the convex hull that's as far in this direction as possible, as I've said. And we know that it's kind of monotonous, right? So if we start at a certain point, so if we try to move forward and look how the distance, how the dot product changes, what we will see is something like this. It may increase so that we reach the maximum here. Then it will decrease again when we travel the other side of the polygon, and then it will increase to this value. Okay, so this is kind of nice, but also the usual approach that we use to find maximum of similar looking functions is like binary search or ternary search. Still, neither of them are going to work when this happens, basically. But we still want to do something like binary search, and well, let's try and do that. So the only way that keeps us from getting a correct binary search is that this happens. Okay. So, well, let's try and get rid of that. What we are going to do, basically, is to split our range of vertices into some smaller ranges, or find some smaller ranges, so that the binary search will work for them. Okay. So how can we do that? So let's see. For example, one approach is to choose a certain point, and well, then let's assume that we cut the polygon with an orthogonal line to our vector. So that splits our polygon into two ranges, right? And in both of these ranges, we can then apply the ternary search, for example, or you can go with binary search if you if you are optimizing like slightly different things. Like instead of distances, you're looking at the like the differences of distances, and then you can go with binary search. So the only problem now is that if we have this point, what is the place where we should make the cut here so that it splits into two ranges? And that, like, to find this place where we do the split, here we can go with binary search. Okay, so if we assume that this point has index 0, then and we look at the like comparison pi dot vector ab is, I don't know, at least the dot product of p0 ab. Okay, so we start here and we travel counterclockwise. So in this case, it's like it holds, and then it doesn't hold. Okay, and if it doesn't hold, then it will be the same for the rest of it. Okay, the other case that could happen is that, for example, the 0th point is here. So what happens is, instead of starting with pluses, we're starting with minuses. So so its 0th point is here, then like the line goes something like this, and then we have, okay, this point is worse, so it's minus, and then it's minus, and then okay, this point is good, so it's plus, and then there are pluses. Okay, so there are two cases we have to consider, and in each case, finding the optimal split can be done with binary search. Okay, because we have a range and we have this criterion that only changes once on the whole range. Okay, and that's because the polygon is convex. And then, so we have a range with pluses, and when we have a range with pluses, we know that nothing like this can happen. It will be a function with a single maximum, and then we can go with ternary search or binary search. So yeah, the point is, so the point is, there are a lot of problems that you can solve with binary search on convex polygons, but you have to be careful, because as is, if you start from a random point, you are going to have troubles with the binary search working. So you have to make like a few additional steps to transform this problem into a kind of problem that doesn't have problems with binary search. Okay, so to finish, I would like to share a very neat algorithm that it was actually mentioned on the questionnaire, and I believe not many people know about it. The problem is, if you're given a set of points, again, you have to find the smallest circle, the circle with the smallest radius that covers all of the given points, faster than trivial algorithm. How many people in this room know about? Okay, cool. This is like I think it's a very impressive algorithm, really, because we start with a very simple procedure that's even less effective than just than the trivial one, and then we make it into a linear algorithm basically by magic. So let's see. Okay, so we have a set of points, and well, let's write some function that returns a circle. Well, cover. Okay, cover, and it it takes a set of points. So I'll just write points p. Okay. So what do we do here? So we don't know anything in advance. What we are going to do is to process the points one by one, let this be, instead of P, this will be A, because P will be my point. Okay, so first, we will consider the points one by one, and after considering like a prefix of these points, we will have a circle that is the best for this particular prefix. So at the very start, we have like so the current result is like for the prefix of only one point, we have basically a circle of radius 0 that with center in the very first point. Okay, so then we go over all points, and what happens here? Okay, if the point P is inside the circle C, okay, what do we have to do to obtain the new answer? Nothing, exactly. We have to do nothing. Okay, else. So now we have a certain circle that contains something, and we also have a point P that's outside of this circle, and we want to construct a new circle that contains everything here. So what can we say about this circle? The very first thing that we can say about the circle is that the point P is going to be on the border of this circle. Okay, so it will lie on the circumference. Well, that's really the only the only useful piece of information that we get. But still, we will go like so. Our circle C will going to be the circle that covers a certain portion, and with additional information that one of the points lies on the border. Okay, so we will write another function, I guess. We'll call it cover1 because good naming. So it takes a certain portion of A, like a portion of A. I will not specify here. Basically, every point up to P, and then its second parameter will be a point that's bound to be on the circumference. Okay, so we know that. In fact, instead it's not bounding; it's rather additional information. So this point is guaranteed to be on the boundary. All right, and then we just return C. So this function kind of does nothing. Because we kind of say, okay, maybe this function will know what to do. Okay. Well, let's try to figure out how does this work. Cover1, so we have points here, and then we have a point like Q that is bound to be on the border. Well, it starts pretty much the same. The circle, so the circle will assume that it's a circle centered at Q with radius 0. So now we do the same thing. It's like basically I'll just have to rewrite everything here, because the circle C will have exactly the same meaning, and so now we consider the next point, and if it's inside the circle, then we do nothing. Again, the most pleasant part. And then if the point is not inside, then it is like it's slightly nuanced moment. But if we know that if another point is not inside the circle, then here we will have to find the circle that contains a set of points, and also both of the points, the old and the new, on the boundary. Okay? So here it will be something like everything as before, except that we now call another function that takes a set of points, and then it now has 2 points on the border. Well, Still nothing interesting. Okay, what do you think will happen in this function? Yeah, pretty much the same, except that so the function cover3 will have a set of points, and also 3 points that are guaranteed to be on the border. Okay. Well, I guess it does end at some point, right? So what will function cover3 do? Your best guess. Yeah, we could go to cover 4. But in fact, if we have 3 points on the boundary of the circle, we know the circle, right? Because we can't construct it. So the function cover3 finally does something. So it has some points that it does not even care about. And also points like Q, I don't know, R and S. And what it does is return the basically the circumcircle of this triangle. Okay, so the circle of Q, R, and S. And that's how it goes. So that's the whole algorithm. So it's like 3 useless functions and 1 simple function, which like not too much. The one detail that I didn't mention actually corresponds to cover 2. And one thing about cover 3. So it's important which circle do we start from. So in cover 2, we have to start, since we know that 2 points lie on the boundary, the initial circle has to be the circle that's constructed on these 2 points as a diameter. Okay, so it's something like I don't know, Q plus R over 2, and then the distance of Q minus R over 2, something like that. So that's the midpoint, and that's the radius, and then everything goes as well. Another thing that I've actually messed up is this thing, because or did I? I probably didn't. So my concern was, if you have 3 points, then and you want to construct a circle that's the smallest circle that contains these points, then there are actually 2 cases. First cases is the circumcircle here, and the other case is this case when you have to go like this. But in fact, since we've arrived at this function and we are guaranteed that these points are on the circumference, then this is always the correct answer. You don't want to do this, because in this case, it must be that one of the previous function will not call you with these parameters. So let's try and estimate the complexity in this, right? So this function does constant work. It just constructs the circumcircle, so it works in constant time. This function may call the other function at most linear number of times, and it also does some linear amount of work. So it works in n. This function may call this function at most n times, in the worst case. So this is kind of n squared. And for the same reason, the very first function that we're going to call works in n cubed. Okay? So that is not really very impressive. But here comes the magic part. The magic part is that here, here, and well, here is not necessary, but we might do it anyway. We insert a single thing, and the thing is shuffle A randomly. So here we shuffle, and here we shuffle, and here it's not necessary because we can't exactly improve on this oath of n, but just for the swag, let's shuffle them. Okay. So why does it improve of anything? How shuffling the points can help you? Okay, let's look at this function. So what happens is that we know. Actually, the analysis is not that simple. So if you don't grasp it at from the first try, it's okay. But the thing is, so we have a certain point on our boundary, and all our other points in here. So let's try and estimate what is the expected working time of this function. Okay, knowing that this function that we are calling works in linear time, in the number of points that we are passing into it, and that is mostly smaller than n, because if here we are calling this function on the very first iteration, then here we will only pass 1 point as an argument in our list A. Okay, in addition to the points P and Q. Okay, so let's try and estimate the probability that we will call this next function on the kth iteration. Okay, so we have this. So in our shuffled order, we don't know exactly how which of the k points are going to be the first, are going to be considered the first. So let's assume that it's a certain set of k points that are going to be the first. We don't know about their order, but we don't know that they are the first points, and the order is kind of random as well, right? The thing is, regardless of which set of k points we're going to choose, the probability is still the same. So informally, I would say, well, it doesn't matter, so it's true. Formally, I would say that we can split basically all permutations of a points, grouping them by these sets, and then the answer is like a linear combination for all of the sets of equal values. So so the bound we establish for one set is true basically for the whole answer. Anyway, so assume that some k points are the first, and we are going to consider the last point, right? Because we only care about the kth iteration. So which of these points are going to be the last is random, of course, and all of these points are equiprobable to be the last point, right? Because we've shuffled them. But regardless of that, after what happens on the kth iteration, since the set is fixed, we have a predetermined circle that will contain all the points here. Okay? Regardless of the order that we consider these points in, it will happen. This circle will happen. Okay? So, knowing that, what is the number of points that can trigger the reconstruction of the circle? Okay? So we have like the predetermined point Q here, and also some points here. Another assumption that I'm going to make is that no 4 points lie on the same circle. If I don't assume that the complexity estimates are still correct, they are just slightly more details. But in that assumption, so if no 4 points are on the same circle, then our circle that contains our first k points has like the point Q and also 2 other points. Okay, well, let's say that the point, I don't know, like C and D, right? Oh, we have C. Okay, alpha, beta. Why not? Or maybe I should have gone with Russian letters, just to be fun. So, which of let's see which point could be the last. If one of the points that are strictly inside are the last, so there are k minus 2 points inside. Okay, at least k minus 2. So if any of them is the last, then this circle have already been constructed on the previous step, right? Because we had Q, we had A, we had B, they're all not the last. So this circle is already present on the previous step. So for all of these points, they will not trigger the reconstruction of the circle. Okay, so only the points A and B are going to trigger the reconstruction of the circle. Okay. It is clear, like why only. So basically, if A or B are lost, then we call this function. Otherwise not. Okay, so this is the most important part. So this happens because if, for example, this point is the last in our order among the first k, then since we assume that the answer was correct in the previous stage, then all points k, q, alpha, and beta were in our set. So the circle must be basically the same. And as it happens, the new point is inside the circle, so nothing changes. Okay? So here, only if A or B are last, then we call the next function. So the probability here is the probability that A or B are last. It could happen, so in this case, so the probability here is at most 2, because there are 2 points, over k. Alright? It could happen that the circle is constructed as on q and some other point as a diameter, in which case it will be 1 over k. But the estimate, the upper bound is 2 over k. So now what we're going to do is to apply something called linearity of expectation to estimate what's the expected number of operations we will make in this function. So basically that's some linear work that we have to do here just to iterate over the points, and then it's the sum from 1 to n. So here we have to consider, like, if on the k stage we make a call to the next function, it takes O of k time, but we do it not always, and the probability that we do it is by our estimation at most 2 over k. Alright, so in fact we can cancel this case out and see that this is the sum of some constant values. So the estimate for the expected number of operations for this function is linear. Okay. So if you're having trouble understanding this, then intuitively, on each step, basically, if we make a call on an early step, then it's very cheap for us, and well, it could happen with high probability, but the more k gets, the larger the iteration number. It gets increasingly more expensive, but also the probability drops as well. So these kind of compensate each other, and well, in fact, the expected number of operations is constant. It is bounded by a constant that does not depend on the number of steps or the number of points or anything else. Okay? And to analyze the first function, we basically have to do the same thing, except for now the probability will be 3 over k, except for 2 over k, because we have 3 candidates for the last points that will trigger the reconstruction of the circle. So by applying the same estimate, since we have linear time here, we will do the same thing, except that we will have 3 instead of 2 here, and it will be again linear time expected algorithm. I guess the first time I heard about this algorithm, I couldn't understand why, like, by which magic does it work. But it's, I guess it's pretty amazing and a good showcase of randomized algorithm design, which is actually quite prominent in geometry. You can solve a lot of problems by geometrical approach faster than you would usually do with deterministic algorithms. I would love to give you some more examples, but we are almost half an hour into our lunch, so I guess it's a good time to finish the lecture. And yeah, thank you.